Bidisha from Harishchandra Research Institute. She will speak about torsion groups of model curves over cubic and textic fields. Please.
Thank you. At first, I would like to thank the organizer for taking this nice initiative and for giving me the opportunity. So the title of this talk suggests that today we will discuss about elliptic curve over number fields. So let us start with that. Let K be a given number field and E be an elliptic curve defined over that number field K. It means that the coefficient of the elliptic curves are coming for the given number field K. So now since we know that if the characteristics of the number field is not equal to 2 and 3, then we can modify that elliptical E in terms of Weier's transforms. We are doing that because of easier of the calculation. And then we are taking this set. What is this set? This set is called the set of k rational points of E by taking all points satisfying the given elliptic curve E along with the point of infinity. So why this set is important? Because this set actually forms a group under addition with the identity element O, that O is the point of infinity in the projected plane. So now we know that the set Ek actually an additive group, and by a celebrated theorem of Mordell-Weil, we can say that Ek is not only additive group, it is a finitely generated abelian group. So now we have in our hand a finitely generated abelian group. Then we can apply the structure theorem of group theory, and we can write Ek, which is isomorphic to torsion part along with the R copies of Z. So this R is called the rank of the elliptic curve defined over K, and this torsion part is called the torsion group of the given elliptic curve E over K. So now we have torsion group. So the next question comes that how this torsion group looks like. The torsion groups actually looks like of the from Z mod nz or Z mod nz direction Z mod nz where m divides n. So it means that these are only two possibilities of like torsion groups. So there are only two possibilities, either this form or this form. So though it is at only two possibilities, but if we collect all possible torsion groups, then we define a following set. So what is this set? So only we are fixing a positive integer d, and then we are taking all number field of degree d and all elliptic curve defined over those number field. And then we are collecting all torsion subgroups of those elliptic curve up to isomorphism and putting them in a set. So that set is denoted by phi d. So since we fixed only a positive integer d, then we are getting the phi d in terms of d. So this is nothing but a set. So what information we know about the set? So when d equal to 1, then it means that k equal to q, then measure proves that there are only 15 possibilities up to isomorphism. It means that if we fix k equal to q and we take all elliptic curve over the number field q and take all torsion subgroups up to isomorphism, then we will get only 15 torsion groups up to isomorphism. So next case is for the quadratic case. Quadratic case, Kamni, Kamsu and Momo said they proved that there are 16 possibilities. And for the cubic cases, we know the sum answer, but not in general, full answer. So next question is that does it, is this set is going, we see that, but is it finite? For answering this question, Merrill defined this set. What is this set? This set is a set subset of prime numbers. It captures set of all primes such that there exists an elliptic curve of defined over a number field of degree d, and there exists a torsion element in the torsion group such that the order of that element is p. So why this set is important? Because he proved that this set is finite and he could calculate the what could be the largest element of this set. So the largest element is bounded by this and in terms of the given integer d, and later austerely improve this bound. And once we know this bound, uh, then we can say that phi d is finite and it depends only on the given d, that is the degree of the number field, because this bound is depending only on d. So as we have started that by the result of measure and communicance and momose, that these are growing, but this is actually finite. So once we know, get a finite set, we would like to know the elements of that finite set. So previously only for phi d we could get the few information up to degree d. So then we are restricting the family. So how we are restricting the family? So we are taking all elliptic curve defined over rational number. It means that the coefficients are coming from only over q. So coefficients are coming from q, but we are allowing the torsion groups over degree d number field. So we are taking the satisfying element over the higher degree number field, but we are allowing the coefficient only over q. So in this way we are restricting the family, and we are trying to get more information. But there are some result in this restricted family also by Najman, Enrique and their collaborators. But in general, when the degree is bigger than equal to 7, then we don't know the answer yet. So then we can further restrict our family. So how we can restrict our family? We can impose one more condition on that elliptic curve. Then we can impose the condition, the well-known complex multiplicity condition, and then we can define the same constant over CM elliptic curve. So for the CM elliptic curve, if we want to ask the same question, then also there are some progress. But recently, Clark et al., they could compute from 1 to 12. It means that when the degree of the number field in between 1 to 12. But previously, it was known for 1 to 3, but they recomputed also for 1 to 3 and along with 4 to 12. So their paper actually give information so about the set. So what can be the set when you take the subfamily up to 12? But after 12 also we don't know the we know the set, we don't know the set actually. Then we can take the another subfamily. So how we can take the another subfamily? We can take the model curve. So model curve is of the form y square equal to x cube plus c. It means that the y stress form, so there was some ax type of thing, so here that coefficient along with the x also 0. So in this curve is a CM elliptic curve. So in that sense, this family of the model curve is a subfamily of CM elliptic curve. So let's see what we know about this subfamily. So we are taking the same notation over here. So it means that when we are taking the model curve, then we are denoting it by M, and here the two notation along with the same what we have defined in general, that over K or over Q. So in this talk, we, as I told that, we will discuss about the cubic field and the sextic field. So what is the goal of this talk? So here we are considering elliptic curve and we are taking two subfamilies. So the rational model curves and the model curve. So it means that we are taking a subfamily and Q, whatever I mentioned. And among these two subfamily, this family, we are taking two cases over cubic field and over sextic field. And we are studying this, we will study this set and that this set, and over the general number field also we are taking this, we will study this set where the over cubic field and over sextic field. So here with classification you have seen. So what is the with classification? So with classification means if one element of the torsion set, so from the dash set has been given, so when exactly that group will appear, that depends only on the elliptic curve and the number field. So the reverse question, that given a element of this set, so we should give back the possible model curves. So that is called the complete classification. So first observe this case over cubic fields, rational model curve. But before that, since we have seen that over cubic field and over sextic field, but what about the k equal to q and the quadratic case? K equal to q has been studied by Knapp long back, and he proved that there are only 4 possibilities, and all possibilities are cyclic. So these are the possibility. It means that only z mod 2z, z mod 3z, and z mod 6z. So what about the quadratic cases? Quadratic case, Pallav Kantide, he proved that when the quadratic is, then there are these many possibilities, and you can see that some of them are non-cyclic. So the complete classification means, as I mentioned, that when in particular these non-cyclic cases are occurring, for which model curve, and for which quadratic number field. So for that, if we fix a quadratic number field and a model curve, then we have to give the information about this constant and about this d. So this information has been provided here. So z mod 6z is occurring only when c equal to these two choices and d has to be lie in this set. And similarly, the cyclic cases are occurring in these cases and non-cyclic cases are occurring in these cases. So what about the higher degree number field? So higher degree number field means, so when d is bigger than equal to 3. So in the same paper, he computed when d is co-prime with 1. So what about when d is not co-prime with 1? So that's why in this talk we have considered d not co-prime with 1. So the first two cases when d equal to 3 and d equal to 6 we have taken here. So first see d equal to 3 and we are taking the rational model curve and we are allowing all cubic fields and we are taking this set. So here we can see that z mod 9z is occurring, which we didn't see neither in the k equal to q or not in the quadratic case. So first time z mod 9z is occurring. So when precisely this group is coming? So this group is coming when c equal to precisely 16 and k has to be of this form. And the other cases, there are several options, but these are finite options up to isomorphism. And later we will see the proof of this theorem. So, but now we see that when we are giving more relaxation, it means that when we are allowing the coefficients of the model curve C over the cubic field, then also there are same possibilities, but these possibilities are occurring with more choices. With more choices means, so previously we have seen that z mod 9z was occurring when c equal to 16, but here z mod 9z is occurring when c equal to square and 4c is a cube. So that is the difference. So we have more choices here for getting this torsion group. So here also there are some differences when we are giving more relaxation. So let us see the proof of the first one, that is for the rational model curve. So as I mentioned in the Merrill result, that we are considering the prime elements because the order of the elements has to divide it by some prime element. So here if we can eliminate all the primes up to 5, then we could eliminate many choices. So let us first consider the prime order element where the prime is bigger than equal to 5. So suppose that there exists an element of order q, where q is bigger than equal to 5. Then q has to divide the cardinality of the torsion group, which I have denoted by t. So now we are taking p congruent to 2 mod 3q and along with another condition that he has good reduction at p. It is possible because he has bad reduction only at finitely many places, and Dirichlet times in arithmetic progression says that there are infinitely many choices for this case. So along with these two conditions, we have enough choices of prime. And then we are splitting it where E has the ramification and this is the residue degree. And this is the well-known fact in number theory. And then we are using this lemma. So this lemma says that if we quotient it by a prime ideal, which the prime ideal are coming from this splitting, then after reducing it, we will get an injective map. So that injective homomorphism will allow that if Q divides the cardinality of this torsion group, then Q has to divide the cardinality of right hand side. So why we are taking this? Because we can easily calculate. So how we can calculate is that will come from this lemma. So when P congruent to 2 mod 3, which we took the earlier, that P congruent to 2 mod 3Q. So then we can actually calculate it. So after calculating, we get that this is nothing but P to the power Fj plus 1. And then we are allowing that P congruent to 2 mod 3 and we are getting that this is nothing but this one. And then we have two choices, that Fj either 1 or 3 because of the property of residual degree, and we are getting 3 congruent to 0 and 9 congruent to 0 mod q, and that is not possible. And this is the contradiction, and now we can conclude that there exists no point of order bigger than equal to 5. So then we have to deal with all those primes which are smaller than 5, that means 2 and 3. So now we have calculated what can be the possible torsion subgroups that is the two torsion we are calculating. So I didn't put the calculation here. So similarly for the three torsion also we have calculated, and we get back that these are the choices for C, and these are the choices for the K. Choices means these are the property of the K and property of the C for which we are getting three torsion. So now what is the power of 2? So if we can eliminate power of square of 2, it means 4, then we can eliminate the above power also. So first we have eliminated the power of 2. So after eliminating square of 2, and but we have seen that z mod 9z was occurring, so it means that we have to consider square of 3. So square of 3, that is 9. So that is occurring only when c equal to 16 and k has to be of this form. And I didn't include the proof here. And then the higher power of 3, that is 3 cube, and since 9 is occurring, then there is a possibility of 9 into 2, 18. So those two cases also we have to eliminate. So now the remaining cases is 2 into 3, that is 6. So now we have to calculate the all possible element of order 6. So that we have calculated, and this finishes the proof of the theorem. Because first we have eliminated all primes bigger than equal to 5. Then we calculated 2 and 3. Then power of 2 we have addressed. Then power of 3 we have addressed. Then the product of 2 and 3 and product of 2 and 9. And the higher power of 3 we have eliminated, and product of 2 and 3 we have calculated. So in this way we are getting back all the possibilities of the rational model curve over cubic field. So as I mentioned that over sextic field also we will consider. So let us see the sextic field. So sextic field means the degree of the number field is 6. And the first we are taking the rational model curve. Then as we have mentioned in the quadratic case also, so we have witnessed in the quadratic case non-cyclic cases. So here also we can witness non-cyclic cases, but involving Z mod 9Z, which we didn't see earlier. So when precisely these groups are coming, so the cyclic cases are coming for these cases. So it is depending on the omega cube root of unity, and some cases it is depending. And this is the Z mod 2Z, the last cyclic cases. The rest are non-cyclic cases, and non-cyclic cases are coming for this property has to be involved in C and the L, that is the sextic number field we have taken. And if we give the more relaxation, that we are allowing the coefficient of, from the sextic field, then we can get the higher degree torsion group, that is Z mod 19Z, Z mod 7Z, and this Z mod 7Z we didn't see earlier, and this also we didn't see earlier. So here we are getting some higher order element. So if we give the more relaxation, then over higher degree, then we may get some more groups, but we may not get. And these two results in sextic field, and these are the references. So this is the Clark et al. Paper, which I mentioned that where they have computed all CM cases from 1 to 12. And this is the NAP result. And well, on the first model curve over Q, they have computed. And this is the result of Pallab Kantide, who calculated over quadratic number field. Thank you for your attention.
Let's thank the speaker for excellent talk. So, are there questions for the speaker? So if not, then I have just a very short question. Is there something known about the torsion subgroup of the elliptic curves over quintic fields, maybe? Okay, and there is also one question which says that is there any result for D greater than 6?
Yes, so as I mentioned that when D is co-prime with 6, then that is coming similarly. But when D is not co-prime with 6, then still there is no result. But we are trying to prove some cases for some specific cases when D is not co-prime with 6. But till now, as per my knowledge, only these two has been addressed.
Okay.
So I assume that this question is for the model curve. But for the CM curve, up to 12 is known. And the other cases, they're up to cubic on the some kind of curves. For the quartic cases, also some cases are known.
Okay. So, are there further questions for the speaker? Okay, if not, let's thank her once again.